Hello everyone, welcome to my channel MacPandit Learning Hub. The topic which we are currently discussing is velocity analysis in mechanisms using graphical vector approach. In the last session, I gave you an overview of the procedure to conduct the velocity analysis in mechanisms using graphical vector approach. In this session, we will take up a numerical problem and we will see how can we calculate the velocity of different points on different links in a mechanism. So let's begin. So in this slide, a numerical problem is given here. So let me first read out the numerical problem for you. The figure below shows a mechanism in which AB is equal to 50 mm, BC is equal to 66 mm, AD is equal to 100 mm, and CD is equal to 56 mm. The crank AB rotates at 10.5 radian per second in the anti-clockwise direction. Now what we need to determine, let us see one by one. Determine the A velocity of point C, B velocity of point E given BE is equal to 40 mm, C velocity of point F given BF is equal to 45 mm and CF is equal to 30 mm, D velocity of offset point G given CG is equal to 24 mm and DG is equal to 44 mm, E angular velocities of links BC and CD. Now let us see how can we solve this numerical problem. So the first step in the graphical vector approach is to draw the configuration diagram. So I have listed down the steps here for drawing the configuration diagram. The first step is to choose a convenient scale. So here I am choosing a scale of 1 cm equal to 20 mm. So accordingly the length AB it is equal to 50 mm will reduce to 2.5 cm. BC will become equal to 3.3 cm, AD will become equal to 5 cm, CD will become equal to 2.8 cm. Similarly, BF it will become equal to 2.25 cm, CF is equal to 1.5 cm, CG will become equal to 1.9 cm and DG is equal to 3.5 cm. So let us see how can we draw the configuration diagram. So first we will draw the fixed link, that is the link AD, which is equal to 5 cm. Now this is your fixed link here. Now at point A we will draw AB equal to 2.5 cm at an angle of 60 degree with AD. So this angle of 60 degree, this is already provided to us. So let me draw that line. So we will take a protector, we will keep that protector at point A, and at point A we will draw a line AB of length 2.5 cm at an angle of 60 degree. Now the next step is, with B as center, we will draw an arc with radius equal to 3.3 cm. So we know that the length of link BC is equal to 3.3 cm. So we will take this point B as center and then we will take a compass and mark an arc of 3.3 cm, something like this. Now again we know the length of link CD, right? So which is equal to 2.8 cm. So we already have located the point D in the configuration diagram. So we will now take this point D as center and we will draw an arc of radius 2.8 cm. So let us see. So this is how we are going to do that. Now after that, obviously the intersection point of these two arcs, it will give you the point C. Now what you do, now you simply join BC and CD. Afterwards, let us draw BF, CF, CG and DG in a similar manner. Now, once the configuration diagram is complete, let us move to the next step, which is drawing the velocity vector diagram. Let us see the steps to draw the velocity vector diagram. Obviously, we are going to keep the configuration diagram as it is. So just remember, while drawing the velocity vector diagram, it is advisable to keep the configuration diagram on one side of the page and leave a little space on another side of the page to draw the velocity vectors. So the first part of the problem was to determine the velocity of point C. So we will draw the vector diagram for point C first. So as we have discussed in the previous session, that the first step is to write down the vector equation for point C. So this will give you an idea that which vectors we need to draw. So the vector equation for point C, it is simply given as VCA vector equal to VCB vector plus VBA vector. So while writing down the vector equation, you simply remember that you have to follow the order C to B to A. So now here you can see this point A and D both are fixed point. So VCA vector, it will become equal to VCD vector. In the new vector equation, it can be written down something like this. So this is your final vector equation. Now before drawing these vectors, let us quickly run a magnitude and direction analysis so that we are aware that which vectors are known in magnitude or which vectors are known in direction or which vectors are known both in magnitude and direction. So let me quickly run a magnitude and direction analysis here. So let me just write it down something like this: VBA vector, VCB vector. So one column is magnitude, another is direction. So obviously if you observe here, this VCD vector, it is not known in magnitude, but it is partially known in direction. At least we can say that VCD vector is perpendicular to CD. Similarly, VBA vector, it is known in magnitude as well as in direction. Now why I am saying that VBA vector is known in magnitude? Because the angular velocity of link AB is given to us. So once we know omega for this link AB, we can easily calculate VBA vector something like this. So VBA vector, it will simply become equal to AB multiplied by omega AB. So omega AB here, it is representing the angular velocity of link AB. Right now AB is given as 50 mm, omega AB, it is given as 10.5 radian per second. So after multiplying these two, we will get VBA vector as 525 mm per second. Now let's come to VCB vector. Obviously, since we don't know anything about the angular velocities of this link BC and CD, so the magnitude here is not known to us, as well as it is not possible to calculate the magnitude in this case. But obviously we know the direction. So VCB vector is simply perpendicular to BC. So at least partially we know the direction, that VCB vector will be perpendicular to BC, but still the sense of this vector is not known to us, whether it will be pointing upward or downward. So that we will figure out later on after drawing the velocity vector diagram completely. Now let us see how can we draw the velocity vector diagram. So obviously the first step is to choose a convenient scale. So here we are going to choose a scale based on the magnitude of VBA vector which we have calculated. So VBA vector is 525 mm per second. So I will choose a scale of 1 centimeter equal to 100 mm per second. So obviously this VBA vector, it will simply reduce to 5.25 centimeter. Now a very important thing I am going to mention here: while calculating this VBA vector, you have to substitute the actual value of AB which is given to you. That is, AB is equal to 50 mm. So never substitute 2.5 centimeter That means the scale which we have used to draw the configuration diagram. Always remember, right? So while drawing the configuration diagram, we choose a certain scale, but never get confused. Here we have to substitute the actual values. We don't need to use the scale which we have chosen for drawing the configuration diagram, right? Now once you substitute this value, right, you can choose a new scale for drawing the velocity vector diagram. So the purpose of drawing the configuration diagram was to convey you the direction of vectors while drawing the velocity vector diagram. So this will become more clear later on. Now once you have chosen a scale of 1 centimeter equal to 100 mm per second, obviously VBA vector will become equal to 5.25 centimeter. So to draw the vector diagram, first we have to mark the points A and D. So let us mark the fixed points A and D, something like this. After this, the next step is to simply draw the vector which is completely known to us. So here we know that VBA vector is completely known to us. Now VBA vector, the magnitude is 5.25 centimeter, and obviously it is perpendicular to AB. Now what should be the starting point for this vector? That is the head of this vector. It will be point A. So let me draw the VBA vector. So this is your VBA vector, and obviously in the velocity vector diagram it will be written down as AB vector, right? Now as I have mentioned before that there is a simple rule: if the direction of two vectors are known to us, right, then it is possible to find out their magnitudes. So here if you see that VCD vector and VCB vector, they are known to us only in direction, right? But if we use the direction of these two vectors, it is possible to find out their magnitudes. So this rule you have to remember. So let us see how can we do that. So through B we will draw a line perpendicular to BC, and through D we will draw a line perpendicular to CD. So let me draw a line, right? So this line, the blue line which you are seeing here, which I have drawn through this point B, this is perpendicular to this length BC, correct? Now through D, draw a line perpendicular to CD. So now there will be another line. Now this line which you are seeing here, right, this will be perpendicular to this length CD. Now obviously the intersection of these two lines, it will give you the point C, right? So let us mark the intersection of these 2 points as point C. So now what we are going to do, we are simply going to join point B with point C and point A with point C. Now we can simply measure this length AC. So VCA vector, that is absolute velocity of point C, is nothing. It is simply equal to AC vector. Now once you measure this length, the length, it will come equal to 4.3 centimeter. Now obviously 4.3 centimeter, it needs to be converted back to the scale what we have chosen before. So 1 centimeter is equal to 100 mm per second. So 4.3 centimeter, it will be equal to 4.3 multiplied by 100 mm per second, which is equal to 430 mm per second. So this is the absolute velocity of point C. So this is the answer to the first part of the problem. Coming to the second part of the problem, which was to determine the velocity of intermediate point E on the length BC. So since E is an intermediate point on this length BC, so we will mark a point E on this BC vector. So we have already obtained the BC vector from this velocity vector diagram of point C. So here we will mark point E on BC such that BE upon BC is equal to capital BE divided by capital BC. So here you will measure this length BC from the velocity vector diagram which we have already drawn. So BC vector is equal to 3.5 centimeter. Now from here we will simply calculate BE. So BE, again just remember we are going to substitute the actual length of this BE and BC. So 40 divided by 66 multiplied by 3.5. Now this will become equal to 2.154 centimeter. Now here mark this point E such that BE is equal to 2.154 centimeter. So let me mark this point in the velocity vector diagram. So this point E, it will come somewhere here. Now what you do, you simply join A comma D with E. Afterwards, you simply measure this length. So the length AE, it will become equal to 4.2 centimeter. Again, you convert it to the scale which we have chosen before. So AE is equal to 4.2 multiplied by 100 mm per second, which is equal to 420 mm per second. So obviously the absolute velocity of point E is nothing. It is simply equal to the relative velocity of point E with respect to this fixed point A, right? So VEA will become equal to AE vector, it will become equal to 420 mm per second. So that is the velocity of point E for you. Now let's go to the next part of the problem. It was to calculate the velocity of point F and velocity of point G. Now again, to calculate the velocity of point F, we need to draw the vector diagram for point F. So as I have discussed in the previous session, that one way to understand that which vectors we need to draw is to write down the vector equation. But since we have partially obtained the velocity vector diagram for point C, B, so what we are going to do, we will simply leverage this velocity vector diagram to calculate the velocity of point F. Now let us see how can we do that. Now again, here we will mark point F, such that BF upon BC is equal to length BF divided by length BC, and CF divided by BC is equal to length CF divided by length BC. Now you just remember here, right, that the triangle BCF, right, in the velocity vector diagram, it should be similar to the triangle capital BCF in the configuration diagram. So by the rule of similarity, we are simply making this conclusion that this ratio BF divided by BC, it should be equal to capital F divided by capital BC, and similarly CF divided by BC, it should be equal to capital CF divided by capital BC. Now again, just remember this, that the order of small BCF must remain same as that of the capital BCF. That means the order of letters in the velocity vector diagram, it must remain same to the order of letters in the configuration diagram. Also, we know that BF vector, that is velocity of point F with respect to B, it should be perpendicular to BF, and CF vector, that is velocity of point C relative to F, it should be perpendicular to CF. Now finally, we know the value of BC vector, which is 3.5 centimeter, right? So from here, we also know the length BF and BC. So we will substitute all those values, and then we will simply calculate BF as 2.4 centimeter and CF as 1.6 centimeter. Now obviously, to calculate the velocity of point F, right, we need to find out this point small f in the velocity vector diagram. So obviously, once the magnitude of these two vectors are known, it is very easy to locate this point small f in the velocity vector diagram. So let us see how can we do that. Obviously, first we will take B as center and we will draw an arc of 2.4 centimeter, which is actually going to represent this length BF. And with C as center, we will draw an arc of 1.6 centimeter, which is actually going to represent this length CF. So let me draw that. So once you have drawn these two arcs, so obviously the intersection of these two arcs, this is going to give you the point small f, right? So once you have located this point small f, now what you can do, you can simply join this fixed points, that is these poles A comma D with this point small f, right? So here now you can measure AF. AF is after measurement we have like calculated AF equal to 5.4 centimeter, right? So afterwards you simply join this BF and CF also. So finally you can infer from this velocity vector diagram that the absolute velocity of point F, that is velocity of point F relative to this fixed point A. So VFA is equal to AF vector is equal to 5.4 centimeter is equal to 5.4 again multiplied by 100 mm per second. This is equal to 540 mm per second. So this is how you are going to calculate the velocity of an offset point on any link in the mechanism. Now the same process you can repeat to calculate the velocity of point G, right? So you can see here, so I have repeated the same procedure, right, to calculate the velocity of point G. The only difference is that now you are going to consider two triangles. One triangle will be the triangle CGD, right, which will be a triangle in the velocity vector diagram, and another triangle is capital CGD, which will be a triangle in the configuration diagram. So now again we will calculate this length CG and DG, and we will repeat the same procedure. That means with CS center we will draw an arc, then with DS center we will draw another arc, then we will mark the intersection of these two arcs as point G, and we are going to join this A comma D with point G. So from here we can calculate the velocity of point G relative to A is equal to 3.3 centimeter, that is equal to 330 mm per second, right? Now here I'm going to mention very important point. Let's say like if you are not interested into repeating these steps again and again, that is calculation of CG and DG. So what you can do, you simply know that CG will be perpendicular to capital CG and DG will be perpendicular to capital DG, right? Now here you can realize the importance of drawing the configuration diagram. So you can see here that what you do, through this point C, right, you simply draw a line perpendicular to which length? Perpendicular to length CG, right? So through point C, right, you simply draw a line perpendicular to CG. So this line which you are seeing here is perpendicular to CG, and again through point D you draw a line which is perpendicular to DG. So you can see that this is the point D. Now through this point D you draw a line perpendicular to DG, that means this length, correct? Now you can like see here that once you have drawn the configuration diagram, it becomes very easy to draw the vectors which are known in directions only, right? So now what you do, once you draw these two lines, obviously the intersection of these two lines, it will give you the point G, right? So that is another approach which you can follow, right, if you want to avoid these calculations, right? Now afterwards you simply measure, right, AG, and you can calculate that velocity of point G relative to A is equal to 330 mm per second. Now let us move to the next part of the problem, which is basically calculating the angular velocities of link BC and CD. Once you have drawn the velocity vector diagram and you have calculated the linear velocities of points B, C, G and F, it becomes very easy to figure out the angular velocities of link BC and CD. Let us see how. So obviously the angular velocity of link BC, it will be simply equal to, let me just mention here that VCB vector, it will be simply equal to omega multiplied by the length BC. So let me write down here omega BC. So omega BC, it will represent the angular velocity of link BC. So omega BC is nothing. Omega BC, it will be simply becoming equal to VCB vector, that is relative velocity of point C with respect to B, right? So magnitude of this VCB vector divided by the length BC. So now we know that we can measure this VCB vector from the vector diagram, and we have already actually calculated that. So we will simply substitute those values here and we will calculate the angular velocity of link BC, which is equal to 5.303 radian per second, right? Now this is fine, but let us figure out the direction of rotation of link BC, right? So if you see this, the VCB vector, it is pointing from B towards C. That means it is pointing in the downward direction. So this simply indicates that the point C, right, the point C in the configuration diagram, it will have a tendency to move towards the downward side, right, with respect to the point B, right. So obviously from here we can figure out that this link BC, right, it is going to rotate in a clockwise fashion, right. So similarly we can calculate the angular velocity of link CD. So obviously the angular velocity of link CD is simply equal to what? Again we will formulate the same equation, that is velocity of C relative to D, right. So velocity of C relative to D, VCD vector is equal to simply omega CD multiplied by the length CD. So this VCD vector we can measure from the velocity vector diagram, right, and then we can convert it to a proper scale. So we have already measured this and we have calculated it. So it is coming equal to 430 mm per second. So we will simply substitute those values here. So DC VCD vector is nothing, it is simply equal to this length DC vector. So DC vector is equal to 430 mm per second. This thing we already know. So you simply substitute those values here and then substitute the value of length CD, right. After division you will obtain omega CD as 7.68 radian per second. Now again let us figure out the direction of rotation of link CD. So from here you can see here that VCD vector, right, it is pointing from D toward C. So if you consider the configuration diagram, so let me roughly draw the configuration diagram here. So if you consider the configuration diagram of the 4-bar mechanism, so you can easily conclude that this point C, it will have a tendency to move towards the left side with respect to this point D. So this simply indicates that this length CD, right, this length CD, it is going to rotate in anti-clockwise fashion. So the direction of the rotation of link CD, it will be anti-clockwise. So with this I would like to conclude this session and hope to see you in the next session. Thank you.